All right, let's continue on our adventure with functions. We're going to do some formalizing relations and functions. Kind of sounds like a dating situation, of formalizing relations. A little creepy, but this will be fun. Our objective is to determine whether a relation is a function. So we're going to look at relations and determine if there's a function. We're going to go ahead and find the domain and range. We need to be comfortable with what those are so we can find them. And then we're going to use function notation. To do this, remember, you're going to need some graph paper, so grab your graph paper, your packet. Make sure that's handy. All right, a relation is a pairing of numbers. It shows up as a set of ordered pairs. So we can show up as a relation as a set of ordered pairs. And that would be a relation. As x changes, so does y. As an independent variable and dependent interact with each other, they show different values. The domain in this particular situation, a domain is actually going to show up as our x in our ordered pair or our independent variable. And our range that we see playing out is that's going to be our y values. So that'll show up as our y values, which will be our dependent variable. So we'll be interacting with our domains and our range within a relation. So we're going to identify functions. I'm going to use a mapping diagram to do that. So we're going to identify the domain and the range of each relation, and then that's going to help us determine if it's a function. Now remember, a function has an input with exactly one output. So it has exactly one output. So let's see how that plays out. So let's look at our first one for A. My domains are -2, 0, 4, and 5. And my ranges 2.5, 6.5, and I already have 2.5. And when I look at them, -2 goes to 0.5, 0 goes to 2.5, 4 goes to 6.5, and 5 goes to 2.5. Okay, and our conversation is for something to qualify as a function. For every input, there needs to be exactly one output for this particular situation. So this relation does qualify as a function. So is it a function? It is a function. Let's compare this next one. So I have 6, 4, and 6 is already up here, and 5. I'm going to look at 5, 3, 4, 8. So 5, 3, 4, and 8. And when I compare them, 6 and 5, 4 and 3, 6 and 4, and 5 and 8. So again, I'm looking at every input has exactly one output. In this particular situation, 6 is showing us 2 outputs. So this would be a function. No, it is not. That's what disqualified it at that point. All right, press pause. I want you to give a track on this one. You're going to identify the domain and the range of each relation, and I want you to determine, is it a function or no? All right, you can see the domain is all of our x values. Our range is going to be all of our y values. And if you notice, they do get placed in order too, from least to greatest. So keep that in mind too when you're organizing your domain and your range, using your bars as well to indicate those. And then when we look at this, every input can only have exactly one output, and because of this right here, not a function. The second one, again from least to greatest with the bars, we have our numbers, our domains, we have our ranges, and it is a function because every input has exactly one output. Another way to decide if a relation is a function is to analyze the graph of the relation using the vertical line test. If any vertical line passes through more than one point, so that's a key, more than one point of the graph, then for some domain values there is more than one range value. Now remember, domain is our x, so our ranges. There's more than one y value. So the relation is not a function in that case. So that's showing me that there are 2 outputs. So I plotted these points already, and then I'm looking and taking the vertical line test, and as I run through these, I see one value, one value, one value, and right here I see two values. So right here, not a function, because somewhere in here we have two outputs being played out right here and right here. So you can see it in our points, but it verifies it in the vertical line test. All right, I put my points in here. My x's, we're going to play out my y's, and we're going to plot these out. So I'm going to press pause, fill these in, and we'll see what happens. All right, so when I run my equation, and I have all my coordinates placed out here, I'm going to go ahead and draw my line. And the vertical line test does show me that for every 1 point, there's only one output. When I look at each one of my coordinates, I can see that every input has exactly one output. This indeed is a function. All right, press pause, and I want you to give it a try, and go ahead and use the vertical line test to see if these particular coordinates, this particular function, if they are a function. All right, I plotted the points, and I can tell from my vertical line test that everything is good on this one. So indeed, we have a function over here. And this one here, we run into a situation right there. I've got two outputs that are in the same one. This indeed is not a function, not even if it works hard and tries to become one. You've seen functions represented as equations involving x and y, such as y equals negative 3x plus y. Below is the same equation written using function notation. So here we go, and we're going to switch over to this. Notice that f of x replaces y. It is read as f of x. The letter f represents the name of function, not as a variable. So the function notation is used to emphasize that the function value of x depends on the independent variable of x. Other letters beside x can also be used, such as g and h. And they kind of play out there as like a function of g or a function of h and the such. So we're going to try it out on this one. The function of w of x equals 250x represents the number of words that's happening there that you can read in x minutes. How many words can you read in 8 minutes? So we can go ahead and play this out. Is w, the function of x, equals 250x, and x represents the minutes, so I can times 8. Sorry, I had to pause that. I was running out of ink. And that's going to be like, wasn't that like 5,000? How much does that end up being? It's like 2,000. Yeah, like 2,000. Yeah, 2,000. Or 20 GG, apparently. So it's going to play out 2,000. Finding the range of a function, okay? So the domain, x of x, so we understand what the domain is, so I'm telling you what it is, and our domain plays out as our x, so 1, 2, 3, 4. You've been doing this. We've been building t-charts. We're just getting comfortable with the language behind the algebra, and the range that we're playing out is going to be our y. So we're just going to plug it in. If x is 1, what is y? So let me go ahead and I'm going to pause and fill this in. What I'm going to do is I'm just going to go ahead and substitute each one of these in for my x, and to get my output. Ooh, look at that. It's not magic. It's the pause button. So my range for this one, I'm going to put it in order from least to greatest. My range is going to be my values. That's my range. I want you to give it a try. Press pause. You go ahead and find the range of this particular function. All right, let's see how you did. I have my t-chart here. Notice a couple of details of my range as I've got my bars, and I've got them from least to greatest as well. All right, let's look at this one, identifying the reasonableness of a domain and range. So we have 3 quarts of paint to paint the trim of a house, okay? So I have 3 quarts, so I can't have any more than that. Quart of paint covers 100 square feet. And so we got a function here representing the area in square feet that it covers. We're looking for the domain and we're looking for the range that are reasonable for this function. Well, we need to play through here. Well, the least domain that we can use is 0. I mean, really, the least we can go is 0 amount of paint. So the quarts, and the most we can have is 3 quarts of paint. So my quarts of paint needs to be less than or equal to 3, and it needs to be greater than or equal to 0 for that particular situation. So I kind of know my x and y, and I just kind of need to get started. I can use a quart and a half. I can use decimals, but in this case, I want to keep it nice whole numbers. So let's do 0, 1, 2, and 3 to play this out. So as I plug these different things in with my equation here for quarts, so if I use 0 quarts, crazy. I use no paint. I paint actually no area. Call me crazy, just not out loud. If I use 1 quart, I am going to cover 100. If I use 2 quarts, I'm going to cover 200. And if I use 3 quarts, I'm going to cover 300. I can look at this, and if I graph this particular situation, I can see that it is indeed linear. Well, that graph is so not true, because it does go through the origin because of 0, 0. So my graph is going to look something like this. It is linear. It's a reasonable function. For every input, there's exactly 1 output. Awesome. All right. Will you give it a try? I'm going to go write a thank you note to my dentist.